and APS Kerala section. I warmly welcome all of you to the DL on the topic History and Future of Implantable Antennas, handled by Professor Cynthia M Furse. Implantable antenna technology is a current trend in many applications, mainly in biomedical applications. The trend of implantation started in 1960s with implantable pacemakers and is emerging with improving the size and efficiency of implantable devices. So I would like to introduce and welcome Professor Cynthia M Furse, who is a professor of electrical and computer engineering at the University of Utah, USA. She has taught electromagnetics, wireless communications, microwave engineering, antenna design, etc. Her research interests are the applications of electromagnetics to sensing and communication in complex lossy scattering media. She has received numerous teaching and research awards. Moving on with the session, I request all the participants to remain active and attentive throughout the session. Kindly keep your microphones and camera muted throughout the meeting and post your queries in the chat box during the Q&A session towards the end. Please do fill the feedback form provided at the end of the session to get your e-certificate of participation. Handing over the session to you, ma'am.
Hey, well, thank you very much, and thanks for the invitation. I'm going to share my screen and set my slides. So I'm hoping that you're seeing my slides at this point. So I do want to talk about a history and future of implantable antennas. And the reason I'm talking about the history is to actually help us understand the science that is driving the current and next generation technology. You can find several of our publications at emlab.eng.utah.edu if there are things that you'd like to download. So I am a professor of electrical and computer engineering at the University of Utah. Utah is in the western part of the United States in the mountains, and the picture that you see below is very much what we look like right now in early to late fall. The engineering complex is extensive. We have 7 departments in engineering, and electrical and computer engineering is deeply embedded with all of those departments. We do a lot of collaboration. We also collaborate deeply with the medical school. So medical implants are actually, of course, what's driving what's driving implantable antennas. Pacemakers were the very first application of implantable medical devices that required an antenna for communication. You can see right here, there's a pacemaker. It's typically embedded under the pectoral muscle in the shoulder. So it's a battery pack. It's the computer, and a lead, a metal lead, runs into the heart where it's attached and implanted wherever the person needs to have the heart shocked, basically. When the heart is not working properly, it is an electrical device. The pacemaker instead will shock the heart, keeping it beating as planned. New types of pacemakers, however, are very interesting. They're called leadless pacemakers, and both the battery pack, the computer, and of course the electrodes can be implanted directly inside the heart with no connection like you see between the pacemaker, battery pack, and this wire. So having no leads makes this much easier to implant. You can just go up through one of the arteries and basically inject this into the heart. It's a tremendous improvement. Artificial pancreas is often used for people who have severe diabetes to be able to monitor and manage their blood sugar. In this case, you have an implant that's near the hip and then a controller that's nearby that's just carried on the belt. Cochlear implants, which we'll talk about also, are very tiny. They help people hear. They basically can bypass the lack of nerves in someone's ear to be able to give them rudimentary hearing. A similar stimulation system is for deep brain stimulation, and that actually uses the same battery pack that is implanted in roughly the same place as it is for a pacemaker. The lead, instead of going to the heart, goes up to the brain, and then there's a long electrode that goes deep into the brain to be able to do stimulation for things like Parkinson's disease, any type of epilepsy and seizure, and it's even being used in many cases for deep depression. The ability to bypass the ear, we can also bypass the eye, enabling people to be able to have rudimentary sight. So these are just a few of the applications of medical implants, and there are more. All of these implants that I'm showing you are stimulation implants, which means the device on the outside actually stimulates a nerve. But there are equal number of applications for being able to receive information from nerves or organs and being able to control many of the functions of the body that might have been lost. So yes, again, here's a close-up of the pacemaker and the leadless pacemaker. So nerve stimulation and muscle stimulation needs to be done with electrodes. One of the most famous electrode array is the Utah electrode array, also called the UEA. It's a silicon array. It's actually etched. It's 4 millimeters by 4 millimeters on a side. You can see it's very small. There are 10 electrodes down each side, so a total of 100 electrodes. This can be just pressed onto a nerve or a muscle or the brain and be able to read or transmit to 100 different locations. Now, the wireless technology that we use, such as, here's the cochlear implant. In the cochlear implant, there's a coil like this. Each of these little brown spots is an electrode, and that stimulates the nerves of the ear. In order to be able to get into the deep area where we need to do the stimulation, there'll be just a receiver, just an audio receiver on the outside of the head, which will transmit through the skin wirelessly into the area of the head. So we need a transmitter and then a receiver and stimulation. So that would be telemetry. That's how we want to actually transmit data so that we could stimulate these electrodes in a certain way to generate hearing according to the noise that's happening outside. Wireless power transfer is an alternative thing, and that's used to be able to recharge the battery. Down below, there's certainly a battery in all these devices, and it needs to be readily recharged. So there are two different needs in medical implants for wireless technology, both of which require different types of antennas. So in wireless technology, inductive coupling is still the most common way that wireless is transmitted, both power and data. In this case, you generate a current in one coil, which generates a magnetic field, which is picked up by a current in the other coil. This is typically done in the low kilohertz range. Now, there is both an uplink and a downlink in these applications. And one of the important things here is that you will always note that the external receiver coil is very large compared to the internal receiver coil. And that's because a lot of energy actually reaches out to the sides and is lost in the internal coil. And you also need alignment. So the external coil is very large, the internal coil is smaller, and energy is transmitted between the two. The inductive coupling that's used is familiar to all of us in electromagnetics. An oscillator is used, a rectifier is used to convert the current into a receivable voltage, actually, that can be received across the load. It is the most common method that's used today, but it has several limitations, particularly the distance that can be transmitted. Basically, it's an on-skin device to a just sub-skin device. The alignment, being able to get the two coils lined up, the frequency and data rates are low, and the efficiency is very small. There's a lot of loss in the coils and the circuits, and of course the body itself. So inductive links can be greatly improved. So the first inductive link, let's see, it's not there. So here's one of the early inductive links, 1997. You can see that they used a printed coil that allowed them to get many turns. The more turns you have, the more efficient these devices are to a point, because each turn also loses energy just by absorption. So this was a 1997 transmitter coil for a cortical visual implant. It was done at 20 megahertz. By the 2014, there were opportunities to be able to make the coils very small, like 1 millimeter, and still be able to do reception, not so much transmission. The trouble with the very small coils, however, is that they pick up such a tiny amount of energy that it was difficult to get enough to be able to charge a battery or even to be able to transmit data very far. So I actually entered this scenario in 1999. I had a student named Sam. He was a climber, liked to climb rocks, and he was an undergraduate in my electromagnetics class. He missed class for pacemaker replacement surgery, which meant he was out about a week in order to have his pacemaker replaced. At the time, they didn't really have a good way to tell what was going right or wrong with his pacemaker or even the status of the battery. He wanted better communication with the pacemaker, so he didn't have to go to the doctor all the time for these sorts of updates. And he did his senior project on building an antenna for the pacemaker. So the challenge with this is the size versus frequency. We like to stay low in frequency so that the energy can transmit through the body without having an awful lot of loss. But yet we like to stay high in frequency so that the antennas can be small enough to be placed on the implant. So if you imagine a half-wave dipole antenna, which isn't exactly what we're using, but start with a half-wave dipole. A 20 megahertz antenna would be 41 centimeters long. A 403 megahertz antenna would be 5 centimeters in size. So we'd much rather have the higher frequency. However, as I mentioned, the higher frequency has more loss, the lower frequency transmits deeper into the body. Skin is one of the less attenuating of the tissues. It's relatively dry. But even here, you can see that we lose a lot of energy just over a small distance in the skin. So the frequencies are one of the important things that had to be considered historically. Originally, medical implants were in the Industrial, Scientific, Medical, or ISM bands. These were established in 1947, and there were many, many applications in medical and beyond. So the frequencies that were most appealing for these medical implants were 433, 915, and 2450 megahertz. But in 1999, a dedicated medical implant communication services band was established. That's between 402 to 405 megahertz. It was expanded to med radio in 2009 and expanded just slightly to 401 to 406 megahertz. Now, this is a dedicated band, which means there will only be implantable medical devices that are embedded long-term in this particular band. So the industrial, scientific, or medical bands were used so extensively that you're still going to see a lot of data in 433 megahertz because it's the closest ISM band to the mix band of 401 to 406 megahertz. Now, the antenna design, if we were to just use a dipole antenna, it's pretty big to fit on these devices and not ideal. So actually, a better design is the planar inverted F antenna. So the antenna radiator can be any size and shape, and I'll be showing you several different possibilities there. You have a ground pin that basically makes the antenna act like it's twice as big as it really is, and a feed pin that is used to generate the energy on the radiator. The planar inverted F antenna, as I said, can have any shape, and in this case, an example would be a spiral, and it can be placed on the body of a pacemaker where the pacemaker acts like the ground plane. Now, the ground plane is really important because that's what makes the antenna function properly. The shape of the radiator is important. The substrate material, which I've shown here in blue, is also important. As you increase the dielectric property, the relative permittivity of the substrate, you'll end up with a smaller and smaller physical antenna because it looks electrically larger. And then, of course, the yellow material is an insulating material that's used to keep the radiator from shorting out against the body. So when we think about miniaturization, the important thing is to be able to have a way to shrink up this dipole antenna. The first concept that I want to share is the ability to use a monopole instead of a dipole antenna. That's where you put a ground pin on the end, you put a feed in the middle, and the ground basically makes the antenna act like it's twice as large as it is. It creates a virtual antenna to the other side. So that's one of the first miniaturization techniques for implantable antennas. Now, there are several different shapes that we could use. Two that we experimented with extensively were the spiral and the serpentine PIFA. Technically, both of these are the same length, but they don't act exactly the same. You can see the current distribution here on these two antennas. The feed is located up here in the top right. So in this case, the arms that are closest together that would have the most coupling, one has a low current while the other has a high current. On the other hand, in the serpentine antenna, you'll note that the low current antenna area is going to couple strongly to the higher current antenna area. So it's really fairly significant, the difference between the serpentine and the spiral. And we found that the spiral worked better. A serpentine antenna had to be longer and it had more cross coupling. Didn't keep as nice a bandwidth as the spiral antenna. You can tune the frequencies of both of these antennas just by moving the feed and the ground. You can tune both the frequency and also the depth of the reflection coefficient. The lower the reflection coefficient, the better, because that means the antenna is better matched. More power that you transmit gets onto the antenna, or more power that you're transmitting to the antenna directly gets onto the antenna. So it's better. And you can adjust these just by moving the location of the feed and the ground. Now, let's consider the planar inverted F antenna in the body. So the thing about the planar inverted F antenna is it's intending that this is going to be the radiator. But if you were to touch that directly to the body tissues, shown here in pink, it would short out the radiator, and the radiator wouldn't act like an antenna at all. So the substrate, the relative permittivity, is helping us to shrink the antenna. The insulator is going to be very important to not short out against the body, but the body is actually doing us a big favor. As you increase the dielectric of the body tissue, the antenna also thinks it's electrically smaller, much the same way it does with the substrate. So when you put this PIFA antenna in the body, it can actually be physically smaller than you originally planned. So that's pretty nice. And then we also use a superstrate material here as well. So the effect of the substrate and superstrate can be seen here. As you increase the dielectric properties of the substrate, shown here in the blue picture, the frequency of the antenna goes down. That means that it thinks it's electrically larger. And then in the superstrate, the same thing happens. Now notice that changing the substrate didn't change my matching very much, but changing the superstrate changed my match substantially. Although it makes the antenna look like it's electrically larger, it also decreases or increases my reflection coefficient, which isn't necessarily as desirable. So you have to kind of play back and forth and design the trade-off between the superstrate and the substrate for each of your applications. So beginning with the serpentine antenna, the spiral and serpentine antenna in about 1999, by 2004, the spiral had become the norm. So in 2004, there was a special issue in Microwave Theory and Techniques, again, looking at the mixed band. And here was an example of another group's spiral antenna. Many different spirals were designed, and some of them were stacked, some of them were thicker, thinner, all different designs. But the spiral antenna had kind of become the mainstream by the early 2000s. Here are several other PIFA antennas that you might see. So you can make the different arms fatter and thinner. That actually affects the matching quite a bit. So this is another way of tuning up the antenna. The serpentine PIFA was used in a different way than the spiral PIFAs. Now in this, it was used for continuous blood glucose monitoring. In this case, the antenna was not used as the transmitter, it was actually used as the sensor. So as the electrical properties of the blood changed, it would change the impedance of this antenna, which would allow you to be able to measure blood glucose with this antenna itself. So again, the spiral antenna was used, the serpentine antenna was used here, but for a slightly different application. The spiral PIFA was also used on the body of a rounded pacemaker. By 2011, the designs had become relatively standard at this point. But then we started seeing three-dimensional antennas. Probably the reason we were seeing three-dimensional antennas was it was much easier to simulate three-dimensional antennas by the time we got to the mid-2000s. So here's an example of an antenna that would be integrated with a cylindrical device that would be able to be injected, such as into a capsule. So an endoscopy capsule, for example. And you can see that the antenna is a spiral antenna still, but it actually spirals in 3 dimensions, a little bit like a helix. Here's another one, and this was put around the human knee. And you can see that it's a 3-dimensional design that's also kind of squiggly. And then finally, here's a flexible antenna that has 2 loops, kind of loop antennas, spirals that are attached to each other. So we've started seeing 3-dimensional antennas for different applications. In many cases, these were much higher frequencies, like here's the 2.4 to 2.48 gigahertz. That's the medical implant. That's the ISM band. And the other 2 are mixed bands. There are many other shapes too, and we and others have done several different shapes. This is one of the most entertaining. This is a genetic algorithm PIFA. It's still a PIFA because it has a ground plane underneath and it has a feed and sometimes also a ground pin. And so it's just a different type of PIFA. And you can see it looks kind of like a random waffle, and it is relatively random. The way you make these antennas is you take a mother antenna that with a random collection of metal in different voxels, and you take a father antenna and you cross them, you breed them. If the mommy has metal and the daddy has metal, the baby's going to have metal there too. If they both have air, the baby will have air. And if mommy has metal and daddy has air, then the baby's randomly going to have either metal or air. You add some natural selection to this. You breed a bunch of babies. You see which ones are the best. You throw the rest away. You continue to breed these generations of babies until you end up with an antenna that acts ideal for your application. You, of course, have to decide what you mean by ideal. This antenna, for example, can be about 2/3 the size of a regular spiral antenna and still do essentially the same job. The thing about these antennas is we don't thoroughly understand them. You can look at this antenna and say, wow, great antenna, it's working well, but if I change something, what will happen? And the truth is you don't really know. We've done a little bit of work on that, and we do know that these antennas kind of have a backbone, like their largest connected section represents the lowest frequency, but still, mostly these antennas are designed with this machine learning genetic algorithm, and it's not easy to predict if you make a change to them, how that will change the antenna, unless, of course, you simulate that. Well, so that's what's been done with pacemakers today. Today's pacemakers are about 2 to 4 centimeters on a side, give or take a little. But the next generation is looking at being able to do pacemakers and other devices that don't have leads, like the leadless pacemaker. In the case of the Utah electrode array, we're trying to get down to something that's 4 millimeters square. The goal is to be able to, let me see if I've got a picture of this. No. The goal is to be able to attach battery, computer, and electrodes all in one very tiny package on the order of 4 millimeters. This can be enabled because battery technology is improving so much. It's actually the electric car that's bringing about the huge changes in battery technology that are enabling things to have much better battery for much smaller size. So that's going to positively impact us on the medical implants as well. So think of antennas that are originally 2 to 4 centimeters in size and trying to get them down to something that's less than half a centimeter. So if we were to consider 403 megahertz roughly in the middle of the mixed band, at free space, that's a 36 centimeter wavelength, half wavelength. In the body, that's 5 to 6 centimeters. But how do I build an antenna on 4 millimeters? If I try to just spiral up my coils and make them that tiny, I could tell you it's so inefficient and so minimal power transmission that's not an effective design. So we need to think of some better ways of having direct transmission to a very, very tiny medical implant. And here comes the next generation. So there are many ways that people are starting to think about doing this. One that our group is looking at is a tattoo antenna. So I'm kind of going to challenge you to think outside the box here. If we have a medical implant, such as shown here, a pacemaker, that has an antenna all on the pacemaker, that's great, but that pacemaker real estate, the size of the pacemaker is what limits the size of the antenna. But that pacemaker's in the body. The body's big. Right? The body is so much larger than the pacemaker or the next generation pacemaker. Why don't we consider using the body structure itself to support the antenna? And that's the concept here. Now, the body is made up, of course, of skin. Underneath your skin is your fat, and then muscle and bone under that, and other organs as well. Fat is an interesting tissue. Fat is relatively insulating. Like you might think of semiconductors, fat is a semi-insulator. So the semi-insulator of fat could potentially support an antenna. So thinking about a tattoo, you could tattoo, using a needle and inject in conductive material into the fat layer, and it could be large relative to the antenna that's below. And then the feed system that's implanted on the device can be very small, with the bait antenna actually being at the surface of the body. Coupling through a few centimeters of tissue is what connects the implanted feed to the surface tattoo. So that's a capacitive or inductive coupling there. So the concept here is don't limit yourself to the real estate of the 4 millimeter medical implant. What else can we use to be able to do a larger antenna? So there are a number of materials that are available for medical implants and more coming. The material science community is absolutely growing the possibilities for biomaterials all the time. So as antenna designers, it's pretty exciting to kind of follow the biomaterials that are available. Now I've included copper tape here just because that would be what we'd use for a gold standard. If we wanted to be able to have kind of the best antenna, we could consider copper tape being one of those possibilities. Copper mesh is something that we looked at because if you were doing a tattoo, you would not have all of the parts of your tattoo electrically connected. So it'd be a little bit more meshy, and you'd have more of the fat in between each of the places that you tattooed. gold nanoparticle mesh is what's shown next, and that's below. That's kind of the darker one. Gold nanoparticles are really interesting. They can be attached into polymers, producing these highly conductive and very biologically compatible devices. Copper is not biologically compatible unless you fully encapsulate it. So the gold nanoparticle mesh is a very interesting material. Then we also can consider various types of inks, paints, etc. Now, inks and paints, most inks and paints today are not biologically compatible. However, an ink or a paint is basically just a material such as a conductive particle that's suspended in some kind of paint material. Now, the paint materials could be made biocompatible. The conductive particles could be suspended in them. So it is possible to also have conductive paints, glues, etc. So these are roughly the types of materials that are available. And again, the specifics of each one of these is becoming so much, there are just so many more options. So let me show you how these various materials stack up. So again, remember that red, that's copper, is considered our gold standard. So that's right here. We're getting a reflection coefficient in free space of about -35. If you go to copper mesh, that's the green, that's very similar. So just going to mesh didn't change our antenna very much. Dropping to the gold nanoparticle material that we're using did drop our reflection coefficient a little bit. We had a little bit more loss, mainly, I think, because of our ability to connect onto it. This material is very thin, very fine, and it doesn't take solder as well. So that was a little harder to connect onto. And then notice as we go to the paints and inks, they still work functionally as well, but they are more lossy. So basically, we found in this kind of study that we needed materials that had conductivity on the order of 10 to the fourth in order to act pretty much like the copper for our antenna. So we tried a tattoo antenna test where we weren't using a tattoo material, we're actually using a conductive ink, but we were treating it like a tattoo. We embedded it in between rat skin. That's kind of this yellowish thing you see here. It was the skin of a rat that had been preserved in a yellow material, a yellow fluid that we then put over a pork loin. The reason that you use pork is because that is electrically the most similar to human tissue. So pork is a good substitute for human muscle. And then we embedded the antenna in between these two. And we were in fact able to make a viable antenna at 433 megahertz. When we considered the copper tape versus the gold nanoparticle material in this particular application, we were actually able to get very, very similar responses with this tiny, thin gold nanoparticle material and the thicker, heavier copper material. So again, able to build a very viable antenna in the frequency range that we were looking for. It's interesting to look at the current distributions, because if we were considering an antenna, and I'm showing you, so this is an antenna that has several slits. The reason there are the slits, it's not because I wanted the slits, but I was imagining if we had a tattoo, it'd be very possible that you would have holes in your antenna where you wouldn't have complete connection. So we were looking at the current distributions of these antennas in several different cases. The top one on the left is in direct contact with a pork, and you can kind of see that the current really doesn't go out to the end of the antenna. So we are getting a lot of shorting out where the antenna is transmitting the energy directly into the pork, but very, very close to the feet of the antenna. If we then going to the right, put a insulating material, so this is 0.1 millimeter of plastic coating, you can see we're starting to get further out to the end of our antenna. As we go down into the fat layer, notice that the fat layer is actually doing a really good job carrying the current to near the end of the antenna. And if we were to use a plastic coating plus the 3 millimeter fat layer, both of those are really quite good antennas. So the fat layer is doing us a big favor in this case. So we really want the antenna as embedded in the fat as possible. So one of the new materials that we've been experimenting is developed by Huanan Zhang, and he's in our chemical engineering department. It's a thermally activated biopolymer. So a biopolymer is something that has two materials, kind of like epoxy. And when those materials are separated, the polymer acts like a fluid. But when the materials are connected or touching each other, mixed together, then it goes to a gel. You can control the gel by how much of which of these two materials you have, much like you can with epoxy. The way you make this material thermally activated is you encapsulate one of the materials in little tiny bubbles, basically little glass bubbles, and you just let them float around. So as long as the bubbles are encapsulating the second material called the crosslinker, then it acts like a fluid. And you make the bubbles just the right size so that when you add heat, the bubbles break, releasing the crosslinker and allowing the material to gel or even completely solidify. The goal in our case was to make the gel have essentially the same mechanical properties as the area where we would want to be injecting it. So if you kind of just feel the skin on your arm, you can feel that it's soft, but yet it's pliant, but yet it's kind of got some stiffness to it. So that's the mechanical properties that we would like this gel antenna to have. It needs to be a biopolymer so that it is biocompatible, of course, long-term biocompatible. And we also need it to cross-link to the right level to be just the right kind of solid, but we also need to do it quite quickly because if you inject a fluid, it immediately starts to dissipate within the body. So you want it to gel and solidify before your antenna kind of seeps away into the rest of the body. So here's an example of a thermally activated biopolymer that's being worked on by our colleagues in chemical engineering. So we evaluated this polymer using some other technologies. The RFCA, or radio frequency cardiac ablation probe, is commonly used for cardiac applications. Like if somebody has plaque in the arteries of their heart, they'll use this probe to be able to, go remove that plaque. They can do electrical changes to the heart with this probe and so on. So it's basically a heating probe that's an open-ended coax. So it's in the 350 to 500 kilohertz RF range. And we used a vial of polymer. We put this probe in, and then we just added heat to the probe. And I know it kind of like splits here just because of the optics, but right here's an example of one of the solid droplets. Here's a droplet we had made a few minutes previous. And this would solidify our polymer very, very nicely. It was important that we tried several different frequencies because the polymer does not solidify the same at all frequencies. We, in fact, also tried HIFU, or high frequency ultrasound, but the polymer is too clear and the HIFU didn't solidify it at all. So we used this 350 to 500 kilohertz probe, found excellent thermal activation and solidification, and said, aha, this is a good material for us. So I'm going to just play a video of this probe, and I'll tell you when it's starting and when it's finishing because I don't have the audio connected for the video. So currently the probe is active. Notice, do you see the little bit of solidification happening here? It's quite fast. It's quite effective. And there we go. Okay, now we've turned the probe off. So you can see that solidified relatively quickly enough that we can imagine being able to use this in an implantable antenna application. The speed, the solidity, and also the electrical properties are things that the engineers in chemical engineering work out for each individual mixture that they create. So imagining that we're able to have a material that is electrically conductive, that is biocompatible, and that can be injected. Let's imagine what we might do with that. One example that we've imagined in our group is, let's suppose that we've got a little tiny implant down here that we want to get power to. If we were using an antenna outside the body someplace, maybe a plane wave is being produced from an antenna far away, or maybe there would be an antenna in the surface, under the surface of the skin in the fat layer, the power is still very spread out at the surface of the body. If we were able to somehow focus it down deep where our implant is, we would be able to receive power much better with that little tiny antenna that we can produce on the implant. So here's an example of the implant, and we've actually used a needle and imagine injecting a metallic material here. And what that does is it focuses the energy right here where we want it. So if we could use this material, make like a three-dimensional antenna that's like a bent dipole, then that can receive the energy from a larger area, focus it down near the feed point. These don't have to be touching the device, they just need to be pointing at it. You're using a couple of electromagnetic concepts here. One is, of course, a V dipole antenna, and then also the fact that electromagnetic fields concentrate on tips and they concentrate on narrow gaps. So we're able to basically make a field concentrator with potentially biocompatible materials. we could increase the power at the implant location by 16 times, or perhaps even more. So this is how 3D printing in the body might work. You could use a generator outside the body. You could have an open-ended coax, which could be injected into the body. It could squirt the biopolymer out through the internal center conductor, and it could heat it as it goes, much like this. The picture is being shown. So we have a microwave applicator, we have a biocompatible material, and then we have potentially a three-dimensional antenna. So let's think a bit more about the next generation antennas for medical implants and how they might be used. Oops, I guess that's it. I can move myself up one more. So we have many applications today. Most of the applications today are still limited by the size of a battery pack that is roughly 2 to 4 millimeters on a side. But there's a lot of demand for being able to go much smaller. The smaller you can go biocompatibility, the smaller you can go, the more medical applications you can do, and the more effective many of your medical applications can be. Imagine, for example, if we were able to do medical implants in the brain, where you could just inject in the brain, potentially even coming up through an artery in the vein itself, and not have to do the full open brain surgery that happens for a deep brain stimulator. So being able to make our antennas much, much smaller is a very important feature, and it's definitely what's happening next. In order to do that, we have to think outside the box, because being able to build these antennas on the tiny battery packs themselves is not realistic. Instead, we need to have other ways to use the body to be able to incorporate antennas that can be large enough for the frequencies that we want, but yet small enough for the medical implant that we want to produce. So I'd love to answer your questions at this point. Let me again mention the website emlab.eng.utah.edu, where you can pick up more of our publications if you're interested in reading more. So thank you very much, and I would love to see questions. I think there were some in chat. Let's see. Okay, let's see.
So now moving on to the Q&A sessions, participants can put their doubts in the chat box.
Okay, so I see some already. One question I see is, how efficient is the recharging in wireless power transfer? I'm going to say extremely inefficient. If you can get 10% efficiency, you're doing extremely well. Part of the reason for that is that your implant is several centimeters deep, typically, or even just a few centimeters, and your antenna is relatively small. The antenna on the outside of the body, which is often held literally on the surface, like it's a box that a doctor would put right against your shoulder, that antenna has to be very large so that the fringing fields between these two antennas can be picked up and transmitted. So the recharging is very inefficient. You've got problems with alignment, you've got the size, you've got the body is a very absorbing, highly conductive material. So the efficiency is very small. And unfortunately, that's true for the data antennas as well. So when I joke and I say, the antennas in the body, medical implant antennas, are actually terrible antennas. We're just trying to make them less terrible. Let's see, how is the radiation from the device taken into care without harming the human body? That's an excellent question. So the radiation from electromagnetics is very different than the radiation from X-ray, of course, as we all recognize. X-ray is high enough power that it's actually able to break the cells, whereas microwave energy is not. So they're very different. So when we use the word radiation, realize we are specifically talking about electromagnetic radiation. Now, there have been huge numbers of studies on the safety of electromagnetic radiation, and there are not issues like the cancers that you would see with X-rays. The most significant thing would be if you made it too hot and burned the body. Cooking definitely is a bad thing. So we need to keep it well below the heating range. And because there has not really been significant data on medical harm, it's very difficult to decide what we should call safe. If something is safe, you can never prove that something is absolutely safe. You can only prove that it's dangerous and then go below those levels. And the only danger that we can actually prove in electromagnetics is the heating. So the guidelines that were created are based on something called specific absorption rate, which is absorbed power in watts per kilogram. It's how much power is absorbed in a small region of the body. Now, there are full body SAR regulations. They're not actually as important to our implants as the localized SAR regulations, because that's what impacts implants more. So medical implants use one of two guidelines most often. The IEEE ANSI, the US guideline is established by the Federal Communication Commission, uses SAR of 1.6 watts per kilogram over 1 centimeter, about the size of the end of your pinky. And that needs to stay less than 1.6 watts per kilogram. The CENELEC guideline uses a 10 centimeter square, which is about the size, 10 millimeter, which is about the size of your thumb. So these guidelines use very localized absorbed power regulations. When we consider an implant, the power is going to be the very strongest, right closest to the antenna, of course, dissipating very quickly from there. It's another of the reasons that we have to use a superstrate material for all of the antennas. When you see the antenna shorting out in the body, that means that it is putting energy directly there at the feed point, which means the energy is highly concentrated there. We have to keep that within these SAR guidelines, so we're not allowed to put very much power into the antenna at all. So when I was showing the examples without a superstrate, for example, that's a very poor antenna because it's very inefficient. It's also an antenna we would have to keep the power very low in order to stay within the radiation guidelines. So the important thing with these antennas is to get the power to spread out quickly and not stay right by the feed point and be too localized. So the radiation from the devices is taken into account with the SAR, or specific absorption rate guidelines, and that those guidelines are meant to keep harm from happening in the human body. So someone is mentioning here, it takes more time for medical doctors to accept biomedical engineering findings. Oh, very interesting. So having worked with medical doctors, one of two things is going to happen. If you're working on a new medical technology, it takes a very long time to get that certified and through the medical device processes where it can actually be certified and used. It's a very expensive, very time-consuming process. Typically in the United States, that takes 5 years or more. So it's very expensive. So a small company can really struggle bringing a medical device to market. And that's why you see most of the medical device companies are large, significant, have a lot of support behind the time that they are spending trying to get a medical device to market. On the other hand, medical doctors are willing to try just about anything. So an example would be there are applications that medical doctors, that there are many, many applications in medicine that are based more on experiment than they are on engineering. So if you were to put, for example, a medical stimulator in the hands of a doctor trying to care for a very ill patient, what they'll do is they'll put the stimulator in, they'll implant it, and then they just start experimenting with the currents and current patterns that are allowed, and they find the one that works the best for their patient. And although that's based loosely on engineering, it's really based more on experiment with the individual patient and the individual location. So I think you'll find that in many cases, medical doctors are perhaps more inclined to accept these technologies than the certification processes even would go. So it takes a long time to get something certified so you can sell it. But once you give it to a doctor, they are pretty likely to just want to be able to experiment with the individual patient to get the best possible outcome for that patient. So you're going to kind of see this dichotomy in the stress that a medical doctor has trying to care for a patient with a serious problem. Let's see. Okay, so here's a question. Can we use a sticker antenna instead of a tattoo, as both are external? Well, the tattoo antenna is actually internal, but it's just subdermal. So a sticker antenna is on top of the skin. A tattoo antenna is just below the skin. The interesting thing is that both of those antennas act extremely similar. The skin is dry enough that that little bit of region between the skin, the little bit of region of the skin doesn't change the antenna very much. So for the design purposes, a sticker antenna that's on the surface and a antenna that's in the fat layer are very similar, not identical, but very, very similar. So can you use both? Can you use either of them? Yes, you can. In fact, if you Google tattoo antenna, the tattoos you'll find are actually the external sticker tattoos, kind of, like children would have that they might play with. So yes, both of these antennas can be used effectively. Both of them are very similar. The difference, of course, is that a sticker on the outside of your skin has to be replaced regularly. So a sticker antenna would be very suitable for short-term applications, whereas the tattoo antenna would be better for long-term applications. Okay, so the challenges of the tattoo antenna, and how about the stability of the tattoo? Well, the truth is, a true tattoo, the kind that's made with the injectable needle that's just vibrating, like a real tattoo if someone were getting a painting on their body, that actually has two major challenges for biocompatibility and biological applications. Originally, we were very optimistic because you can get highly conductive biocompatible tattoo inks. And most tattoos are really very stable. So if somebody gets a tattoo on their arm, it's likely to stay there for life. It does seep a little, it does spread out a little, but not very much. And the reason for that is that these are little particles of material, whether it's conductive or not, and they get encapsulated by kind of the body processes of just holding things in place. They're basically held in place by a type of scar tissue. So they are very stable. But the trouble is, the reason they're stable is this encapsulation. And that makes it so if I used conductive inks, each of those conductive inks particles gets encapsulated by biological tissue. Biological tissue is not as conductive as the encapsulation. So you end up with isolated like dots in your tattoo. They may be very close together, but they're not touching. So if you just try to do a injectable antenna, uh, sorry, not injectable, but a tattoo antenna, it's very conductive when you first put it in because these materials are touching each other. But then over time, like not even very long, couple of weeks, it ceases to be as conductive because of the encapsulation of these particles. So it's very stable, it's not very conductive, and that's why we end up going to the injectable concept instead of just the tattoo concept. If you wanted an antenna under the skin, a better way to produce it would be to use a needle, just inject where you want that antenna and back the needle out. And then you can actually produce a solid that the whole solid gets encapsulated as opposed to the individual particles. So yeah, very stable, but not actually still ideal. What kind of feed is used in the serpentine antenna? So actually in all of the PIFA antennas, the feed is like a coax where the battery pack is the ground, a hole is made, and then an inner conductor comes up through the hole, not touching it, comes up through the hole and makes contact with the serpentine spiral or genetic algorithm or any other shape of antenna that's at the top. So the feed is just typically a coax, very similar to the feed that you'd have on a patch antenna or any other PIFA. Okay, so batteries. What types of batteries and cells are used for these types of antennas? So at the moment, the lithium ion batteries are still the most common in medical implants, but with changes and increases in battery technology, you can expect to see those coming into the biological applications as well. There also are some biological batteries that have been proposed so that the battery itself didn't need to be fully encapsulated. In the case of all of the other types of batteries we have, they're not biocompatible by a long shot. And that's why they're inside the metal structure that you see that is the pacemaker battery pack. The battery pack itself is typically titanium, which is very biocompatible. And then these less biocompatible things, such as the batteries, are housed inside it, and then they need to be sealed in such a way that the fluids cannot seep into this battery pack over the period of, say, 20 to 30 years. For the point of view of mechanical and material science engineers, that's a really good challenge. For those of us in electrical, we have to just trust that our batteries are not going to be short-circuited. So again, new types of batteries are going to find their way into the pacemaker. There is not yet a device that's 4 millimeters square that includes the battery pack. It's just headed that direction. What's the drawback of using a wearable antenna? Okay, I've shown you implantable antennas, and there are even more wearable antennas than there are implantable because it's much easier to get a certification for a wearable antenna than an implantable antenna. If you wanted to do an application where a wearable would be possible, that would actually be better because you would have none of the surgical complications. So you'll find, for example, the artificial pancreas has both an implantable antenna that's under the skin, that's below the skin, and then also something that's just carried on the hip that's like Bluetooth to it. So that's a combination of implantable and wearable. You'll see those a lot. Now, the challenge of a wearable antenna, of course, is trying to keep an antenna on the outside of the body um, in good shape when certainly they're subject to more strains, such as needing to put clothes through the wash, uh, bumping things, they're in the way. Um, People may not, damage can happen and they can be moved. So wearable antennas are fantastic, but they also do have medical limitations. Probably the biggest drawback of wearable antennas, if you were trying to communicate to an implantable antenna, is the shifting of the clothing. So when you put your clothing on and you wear it throughout the day, it actually shifts in general many centimeters across your body. You just move. And so keeping the antennas aligned in clothing and an implant would be fairly difficult. If you can have a wearable there are wearables that monitor, for example, um, all of the body, like your breathing, your heart rate, your temperature, are you alive? So you've seen those in the Apple phone, for example, one of the smaller wearables. So there are wearable applications. They're fantastic, but they do have physical mechanical limits. The How about the replacement if needed and unwanted pickups? So yeah, this is a serious question. So if you had done an antenna that was implanted in the body, that you literally had injected, or that you had tattooed, or that you had opened the skin and laid down, anytime you do a surgery in the body, and there are a surgery where you open and then have to stitch, that's an invasive surgery. A injection or a tattoo would be called a minimally invasive surgery. It would still be considered a surgery. The antenna is going to stay there. And there's not a good alternative for removing and replacing it. So most often, if you had to replace this, you'd have to imagine just going to another part of the body. If you started on the left shoulder, you might, replace this on the right shoulder. So replacement's an issue. Now, how about unwanted pickup? That's actually a very interesting question as well. So unwanted pickup of electromagnetic energy is absolutely what was happening when antennas were used in the ISM band. So the 433, 915, 2450 bands are excellent, but there are a lot of devices in those bands. So the possibility of unwanted pickup was very significant. In this case, it would be taken care of by the electronics and coding of types. So things that you could do with signal processing and hardware filters. That's how the unwanted pickup would be taken care of if you knew that you had a relatively polluted environment. But the mixed band, medical implant communication services band, the dedicated band, is meant not to have things in that band so that you have less external energy that might be picked up. Now, you could still imagine the possibility could be some, but it's going to be very small because all of the mixed bands are for implants, which means it's implanted in my body. And if you also had an implant in your body, we're standing probably 2 to 3 feet, a meter away from each other. So also the proximity of these devices is likely to be very small. We worry more about that when one person has multiple implants, which is certainly a possibility. You might have both a cardiac pacemaker, perhaps a cochlear implant, and maybe also an implantable hormone pump or a artificial pancreas. So having one person with multiple systems is probably where the pickup is more important to consider, or more strenuous, more difficult. And in those cases, again, hardware and signal processing can be our friend to reduce unwanted pickup. I see the feedback form has been posted. Please do give feedback. And then let's see, do implant antenna performance vary in measurement between the dead and live body? Absolutely, yes. The electrical properties of tissue depend very much on how much fluid and salt are in each tissue. So I keep referring to skin as being a dry tissue, and that would be as compared to blood, muscle, brain, etc., which obviously they're wetter. You just touch them, you know that they're all wetter tissue. So the amount of fluid that's in a tissue matters a lot. And then the amount of salts, you can imagine electrolytes that are in a tissue matters as well. So bone has very little electrolyte, whereas muscle, blood, brain have a lot of electrolyte. So each tissue has its different properties. These properties absolutely vary between if the body is dead and alive. So for example, my pork loin, where obviously this has been, picked up from the grocery store, the butcher, uh, all of the fluids have drained out of that particular muscle. A live muscle would have much more fluid. So there is an electrical difference between dead and live tissue. So we generally do simulations in both, and then we compare our measurements of the dead tissue with our simulations to see if we get the same results. We actually measure the electrical properties of every piece of meat that we use because it's also different from individual to individual. And we expect that it's different from time of day to time of day, age matters. And certainly, I mentioned that pork was closest to human tissue. It also varies with species. So the fact that I'm using rat skin and pork muscle, we had to measure the electrical properties of both of those and use them in our simulations for comparison. So how many of these antennas are in practical use? So every medical implant actually has an antenna on it. The majority of them today are the inductive coupling, the spiral antennas. Not the spiral PIFA, but the inductive coupling antennas, just coils using the very low frequency. There are already a number of medical implant communication systems that are used in today's large size devices, 2 to 4 centimeters on a size. There are none today that are in practical use that are in the 4 millimeter range. When you work in academics, you typically are trying to work on something that might be implemented 10 years from now. If you're working in industry, you're probably working on something that you want to implement in 2 to 3, 4 years from now, probably not further than that if you can help it. And then if you're working in the production part of industry, you probably want your product to come out in the next year. So as engineers, we really want to keep our eye on all of those pieces and say, how might this science that I see be used in the next year, in the next 2 to 5 years, and in the next 10 years or so? So what I'm showing you for the next generation, I'm really talking not next year. I'm talking 5 to 10 years from now. Let's see. Are these antennas working in the near field region or over a certain distance? Both, actually. So if antennas are used as sensors, which they are in some applications, they're working in the very near field. You want to sense things that are very close to you. And in fact, when we're doing small distance communications, such as all of the inductive coupling antennas, they're also in the near field as well. Far field antennas is where we'd like to convert from, say, a plane wave down to the medical implant. That's what I was showing you with the possibility of doing a 3D printed antenna. So antennas work both in the near field and the far field, and they do, of course, behave differently in those two regions. Is there work done in the field of implantable rectennas? Absolutely. So a rectenna is an antenna that also acts as a rectifier. I showed you how you'd use a rectifying diode. Well, the antenna itself can act like a rectifying diode. And yes, there is work on implantable rectennas. Much of the same concepts apply, just how you have to implement it it needs to be more biocompatible than it would be for a rectenna outside the body. Well, those are excellent questions. Um, are there any additional questions that I might help with today? Okay, let me remind you about the website where you can pick up the publications if they might otherwise be difficult to access. And thanks so much. I'll be glad to hear from any of you if you have additional questions in the future. How about the safety aspects? Well, there are multiple safety aspects. One of them, of course, is biocompatibility. And that's why when you look at materials, they either have to be fully encapsulated, such as putting them in the titanium battery pack, or they need to be inherently biocompatible. And that's why the work that our material science folks are doing on biocompatible materials is so exciting. So very exciting about the biocompatible materials. And then, of course, you have to meet the SAR, the specific absorption rate, radiation guidelines that I mentioned. So that's another important part of safety. And the third is actually mechanical. So if you implant this battery pack, like I've shown in the chest, under the pectoral muscle, as I mentioned, that's where most of them are implanted today. A person who has that can actually feel it. You can feel this hard metal lump in your shoulder, and people often mess with it. It's just something that we do as humans. So they just, rub it, rub it. It's called the twiddle factor. It often makes this thing turn in circles and eventually breaks it away from the cable. So there are many mechanical safety considerations as well. It's really important to try to be as close to the biological materials as possible. So today's titanium battery packs that are really hard are great. They will get a lot of scar tissue around them because the body's trying to fight them off. They know they're a foreign object. So if you were able to make something that was mechanically softer, then it will be less likely to be fought off. So there's a lot of work that's being done in that area as well. So there are a number of safety aspects. They do all have to be considered. What are the aspects to be focused? Let me see, what was that? Okay, so what would you focus on for future and upcoming research work in antennas? Do you mean beyond implantable antennas or just implantable antennas themselves? Uh, what I challenge my students to think about is we have a lot of antennas. Truly understand the basic technology, the basic concepts that go into those antennas, which is why I started my talk with a history of how we got where we are today. So antennas are just based on the laws of physics and what we know about electrical engineering. So understand that deeply and thoroughly, and don't forget that those laws of physics continue to apply. However, you have to think outside the box if you're going to move to next generation. So look at a problem, take a challenge, such as and we want to have a 4 mm antenna. Can we do it today? What did we do? We first started just simulating our antennas as being more miniaturized. We realized how bad they were. We tried some other miniaturization techniques. They didn't work. Sometimes when you find a problem and you realize this problem's actually impossible, like I can't actually do this with what I'm trying to do today, that's your opportunity for innovation. That's when you could say, all right, it's impossible. Now I'm using impossible loosely here. It's not possible to make an antenna the way we've been doing it today on a 4 mm antenna. We need to think of some significantly different concepts that will allow us to do the application we want within the limits that we have. And that's why I challenged my students to think, what if we didn't have to keep our antenna on the 4 mm box? What if we could use more of the surface of the body? What if we could use more of the internals of the body? So if you're going to look at what's next generation and what to focus on next, choose a good problem that's almost impossible. And then think outside the box and see if you can find some possibilities, some other ideas, some new ideas, that will allow you to move to the next generation. So an impossible problem is actually your best friend in innovation. And it doesn't mean that you can solve it. You can't actually solve every impossible problem, but there's no point in working on a problem that's already been solved. So you might as well go look for some impossible ones. So now, having suggested that you look for an impossible problem, perhaps that's my finishing line here.
Thank you, ma'am. Thank you for taking up the question and answer the participants' queries. Uh, there's one more question in the chat box.
Okay, yes, I see this. Simulation tool and the experimental setup and its initial cost. Oh, yeah. So the simulation tool that we've been using is CST Microwave Studio. It can be gotten academically for very reasonable cost. And sometimes they will even just, contribute it to your lab briefly, at least, to be able to use it. Prior to that, we were using finite difference time domain codes that we had written ourselves. We've used those for decades. So the ability to do biological simulation is really very feasible in today's world. If you want something free, build or pick up a 3-dimensional finite difference time domain code. If you go to the website that I've got below, I've actually included all of our old three-dimensional codes. They are written in Fortran. You would have to convert them to MATLAB. If you do, I'll be glad to post a link to them. But the three-dimensional codes are really important in your simulations. And then human body models are kind of a dime a dozen these days. You can actually pick up an MRI-derived biological model simulation of the human body. The body itself, the structure, eyes, heads, shape, all of that. Those can also be obtained. So you can pick up a simulation tool, build a simulation tool for pretty reasonable to no cost. The experimental setup is more difficult. You need a vector network analyzer. However, vector network analyzers in the 402 to 405 megahertz, you can use the very inexpensive ones. There are some that are about $200, $250. Challenge is they're not as accurate as I would want for the type of research that we're doing. So a good vector network analyzer would be highly beneficial. A poor, or I don't want to say poor, but a lower quality vector network analyzer would be sufficient to start, but you just really need a decent network analyzer. They're available for US $10,000 to $20,000 these days. That's probably our biggest expense. Now, the materials themselves couple up with folks that are in chemical engineering. We haven't paid for any of these materials because it's their experiment as well as ours. And you don't actually need a pacemaker. You can just use a piece of metal. We just frankly use aluminum. You can use a piece of metal that just is similar to the shape and size that you want to use for a battery pack and use that. So I think the simulation tools are very easy to turn up with, but the experimental setup, a good vector network analyzer is important. But that's really about it. It's pretty basic. Thanks for that question.
Thank you, ma'am. Thank you for taking up the question and answering the participants' queries. So now I request everyone to switch on their camera for a photo shoot.
Oh, I love that idea.
Uh, Hello, ma'am. Okay, ma'am. Thank you. I
Yeah,
was just going to request you to stop presenting the screen so that I can capture the
yeah.
photo.
Well, now I can see all my friends in India. I'll also be very glad to stay on afterwards and just, chat if you wish.
So we have reached the end of the session. Thank you, Cynthia ma'am, for taking such a wonderful and informative session on this topic. I hope all the participants found this session informative, interesting, and helpful in building their career. On behalf of IEEE MTTS Kerala session and APS session, and IEEE APS MTTS SBC GCB. We are grateful to have you as a part of this session and looking forward to have you in the future events. Thank you, ma'am.
Thank you very much. I enjoyed it today.
I thank all the participants for attending and being active throughout this session. Please fill the feedback form provided in the chat box to receive your e-certificates of participation. Looking forward to see you in your future events. Thank you.
Thanks so much. Well, thank you for having me today. I'm
Thank
going
you
to go
so
ahead
much,
and
ma'am.
Thank
okay,
you,
Thank
I'm
you.
ma'am.
going to sign off now. Thank you.
Thank you so much, ma'am, for adjusting the time according to suit our schedules here.
It worked out great. Thanks so much.
Good night, everyone. I hope you'll have a really wonderful night and have a good day, ma'am.